Hello, everyone. My name is Aaron Standard. I'm the founder and CEO of Petabridge, and today we're going to talk about message and state versioning. So, this is a really important topic for anyone who's trying to build a event-driven system of any type. But in particular, we're going to focus on distributed event-driven applications, and we're going to talk about Akka.net as the implementing technology behind them. However, all the concepts that we're going to mention here apply to systems that are built on top of Kafka or RabbitMQ, and really any sort of message event-driven system. So let's dive right into our material. The first thing we want to talk a bit about is the message and state serialization defaults that you find in most .NET applications. These tend to be things like newtonsoft.json or system.text.json and that type of stuff. And we're going to talk about some of the pitfalls and problems that those technologies have. Next, we're going to talk about some better approaches for how to handle message and state serialization that avoid the pitfalls and problems we introduced to the previous section. Namely, we're going to talk about schema-based serialization using Google protocol buffers, and we're going to talk about how to version those messages and state objects over time using a very tried and true practice known as extend-only design. And then finally, we're going to talk a bit about how to implement and tool these different approaches using ASP.NET's gRPC tooling to help synthesize C# classes from our Protobuf definitions. We're going to use Akka.NET serialization to talk about how we handle these version changes over a period of time, because it's very easy to control that in Akka.NET. So let's start by talking about the defaults that most .NET developers pick for their applications. Overwhelmingly, most .NET developers opt for an approach known as polymorphic serialization, meaning that the way your type is represented in the common language runtime, which is to say C# or F#, is the way it's also represented over the wire. So the same class is performing both roles of being the application type and the wire type as well. So this type gets serialized using a library like JSON.NET into a JSON representation that can be transmitted over the wire, or maybe it'll be persisted, or maybe it'll be deserialized via something like an HTTP handler inside an ASP.NET service. Polymorphic serialization is the default because it's so easy to use. So it's very ubiquitous. So newtonsoft.json or system.text.json both work very similarly, where they use reflection to translate CLR types into wire types, and they also use reflection, again, on the read side when they're deserializing that wire type to essentially try to fit all the different properties they find when they're, let's say, parsing a JSON payload. They'll try to go and fit those into constructor arguments or onto mutable properties on a C# class. And it's very easy to use, and there's very little upfront work required on the developer's part. That's why it's so popular for the most part. But polymorphic serialization comes with some pretty significant drawbacks. The first big one being is that it's brittle. So if we're using JSON.NET and I have this type inside my application and we wanted to make our messages immutable because that's the best practice, so we decided to make all of my properties read-only and to use a constructor. Well, if I decide to go ahead and introduce, let's say, a new property, this on-margin property down here, and I add a new optional parameter to the constructor, this change is actually not binary compatible. It's what's known as a source compatible change, meaning I can recompile my class without, that depends on this one, without needing to update any code. But the actual signature is different on the constructor than what it used to. And when JSON.NET tries to deserialize this, it'll fail. And you'll get an exception back when this occurs. So if we go and deploy, let's say inside an Akka.NET cluster, a new version of our library that has this constructor change, and we have old versions of the software because you have to essentially replace nodes one by one in a stateful system like the type you'd build with Akka.NET, this is going to introduce a break upon deserialization, where all the older nodes aren't going to have a constructor that matches the new one, and they're not going to be able to process the messages that are being sent to it. And this is one of the major shortcomings with reflection and serialization here, is that ultimately it's brittle. It's very dependent upon the types that you serialize and send over the wire being changed in very specific and meaningful ways. So let's take a look at some examples using the C#9 record type, which is a little bit more durable than these classes with constructors like I just showed you. So if you're working on a greenfield application, maybe one approach you might want to use for trying to version your message and event types would be to go ahead and use records. And that approach does work a little bit better than the previous one I showed you using standard C# classes, but it's still not perfect and definitely not as good as the approach that I'm going to show you. So let's go ahead and take a look at a little demo here that I've hosted on Replit. All right, so this is Replit. This is a sort of lightweight sandbox environment I can use to run arbitrary little programs, and I've gone ahead and built a really simple deserialization demo. So I have a record type that takes two different properties, a name and a count, and these are init-only properties here. Now, I'm going to go and create a new instance of my record here. I'm going to go ahead and serialize that object into JSON. I'm also going to read, of a little file here. This is a previously saved copy of this object stored into a JSON file that is included with this project. So I'm going to read my old JSON as well as the new JSON that's produced from here. So I'm going to write the new and the old JSON out to the console. And then using the old JSON I read from that file, I'm going to deserialize a new instance of my record type, and we're going to print out what those look like on the console as well. So let's go ahead and try running this real quick and see how things look. The JSON should be identical from both the new and the old version. So let's give that a try. All right, so I can go ahead and see the output here. So my new JSON and my old JSON are the same. Thus, my new record, which I created directly via C#, and my old record, which I deserialized using JSON.NET's reflection built into here, looks exactly the same. Well, that's great. Well, now we're going to go ahead and introduce a breaking change to this application. I am going to go ahead and change the name of this property from count to sum. And now we'll go ahead and take a look at what this looks like here. So let me clear the screen from the previous content before. Well, actually, now maybe we'll leave that there. Let me go ahead and try running it. And so now I have the output here. So I renamed this property from count to sum. And you can see that my new JSON has the correct property name on it, and my new object from which this JSON was derived has the correct property name and value. But you'll notice that my old data, which has this count property in it, that data was simply discarded. And the reason why that is because I renamed that property. I went ahead and I renamed it, and now the reflection engine that JSON.NET uses can't match it anymore. Now, there's some worse types of changes I could introduce to my record type if I wanted to in order to make it break. A good example of that would be essentially introducing a property that's not init only. Maybe there's a mandatory property I needed the constructor, in which case I'd be right back to the same sort of problems we had on the previous slide. Records are definitely more robust than normal C# POCO classes are when it comes to wire safety with deserialization, but there's still a better way of doing this, and that's what we're going to introduce in the next couple of slides here. All right, so what are all the problems with polymorphic serialization? Well, the first one that we've just shown is that it's brittle. And that can come in the form of, let's say, the serializer itself, the library being changed, or maybe the runtime underneath it. A good example of that, when .NET Core was first introduced, all of the namespaces for primitive types were moved from one assembly that it had been in for years to another. That really affected users trying to migrate with persistent data who were on .NET Framework, trying to move to .NET Core. That's one example of brittleness. But more commonly than that are things like internal namespace changes or changing the name of a type or changing the names of properties, etc. As you saw from the example with records, we can actually lose data, or worse, you could have deserialization exceptions where the application can't even deserialize any of the old content that was there because no matching constructor can be found. So there's a number of different problems from a brittleness point of view that all come with polymorphic serialization. But that's not all. The next biggest issue with it is that there's a major speed problem. Reflection is really expensive. Reflecting over the types when you're serializing them and when you're deserializing them requires a lot of computational overhead, and it's fairly intensive, and you will definitely see this in a high throughput application. So that's another reason why we might want to consider an alternative. And then finally, there's the security problems, namely CWE 502, which is the deserialization of untrusted data. Now, in systems like ASP.NET Core, which use polymorphic serialization by default, this is largely handled through the model binder. You have a concrete type that the serializer must map to in order for the data to be deserialized. Now, certain types of properties you define on there, such as byte arrays and things like that, can essentially subvert what the model binder does in ASP.NET, and you're back to dealing with this problem again. Essentially, what makes this a security risk is the fact that the reflection system can essentially be nudged to instantiate a dangerous type like a file handle or maybe even launch a process and things like that. So you have to do some extra work to go ahead and make sure that those dangerous types can't be deserialized. On the Akka.NET project, we've actually done quite a bit of work on Hyperion, which is one of our polymorphic serializers that we maintain. And we've made it so this is largely something the user can prevent through a couple of configuration options. But that's another thing you have to worry about with polymorphic serialization. So what's the alternative? Well, the alternative is using schema-based serialization. And the most popular format for this is Google Protocol buffers. It's by no means the only option for being able to implement schema-based serialization. There's other methodologies out there like message pack that are quite popular as well. But protocol buffers are what we're going to use. Now, why would you want to use protocol buffers for serialization and for being able to define separate wire types for your events? Well, the first is that there's no reflection involved, which eliminates all the security issues and eliminates the throughput issues as well. Second is that schema-based serialization and Protobuf in particular compresses very well. If you take a look at the byte layout of a Protobuf message, if you're using something like Wireshark to inspect packets going over the wire, you'll notice that protocol buffers are essentially implemented as sparse matrices. Any field that isn't explicitly populated won't actually be allocated inside the message definition at all. So they compress well. Next is that the wire schema is decoupled from how objects are represented inside your application. This is the most important facet of schema-based serialization, is that we're going to separate our concerns. We're going to make sure that our internal application types don't get reflected into our wire type. That way, any changes that are made to our internal application types are fully decoupled from how they're represented on the wire. This is the real cost overhead of using schema-based serialization, is performing this decoupling. It requires a fairly significant upfront investment because you have to define your wire format and produce it separately. Then you have to write a serializer that can translate between your wire format and your application format. This is not actually very complicated, but it might take a little bit of time the first time you do it. I promise, though, after you go into production with it, the approach I'm about to show you will save you a million times over in terms of different types of risk that polymorphic serializers have. So, for instance, you're not going to need to worry about the underlying serialization format changing unexpectedly as a result of a runtime or a library upgrade. You're going to have the ability to explicitly control how new versions are introduced, and you get a lot more, let's say, separation between the way your code base is implemented and the way critical events and state objects are persisted or described in wire and file formats and that sort of thing. Probably the biggest benefit of Protobuf, though, is its version tolerance. It's inherently backwards and forwards compatible. Now, there's some trade-offs for doing that, namely that just like with records, if we go ahead and see a property that we don't have a definition for in our version of this message, then we're simply going to ignore it and not assign any value to it. That's something that we have to account for in our deployment process for how we think about introducing new versions into our software. But the fact that we have the ability to make sure that those changes can be introduced in a safe way that is also backwards compatible is very powerful, and we can leverage that. Finally, protocol buffers are also platform independent. They're one of the most popular formats for being able to build, let's say, services that interoperate with other services written in different programming languages. So, gRPC, for instance, is built on top of the Protobuf wire format. It's one of the sort of, let's say, legacy technologies that Google kind of leveraged when they were designing it. Let's talk a bit about how Protobuf messages are defined. This is a basic Protobuf definition here. So the way you define messages in Protobuf is you create these message classes. And these message classes contain optional properties. All these properties are optional. The message isn't going to fail to be instantiated if none of these properties are populated. Now, that might create some problems for our application itself because we probably do need these, but that's something we can enforce through our serialization layer that we're going to define. The reason why these properties are all optional, by the way, is just to go ahead and make the read side of the serialization system as tolerant as possible. Now, you can compose message types in Google Protocol buffers, where if I go ahead and create another state object that uses a property that is of type ask, that composition will work. So you can do composition, no problem at all in Protobuf, but one thing you can't do is inheritance. There's no polymorphism in Protobuf, and that's done in order to keep the wire format simple. So it's ultimately in practice not a huge problem, but it's just something you should think about when you start modeling messages here. Now, you might be wondering what these numbers are for. These are the actual real identifiers of these properties or these numbers. So if we take a look at the wire format, we're going to have a descriptor that describes the type, and then we have this integer or short integer. We're going to have this short integer plus a type descriptor here is going to represent the name of that field. So this order ID property, that string never actually gets transmitted in Protobuf. That's one of the compression savings we get compared to something like JSON. You don't need the full name of the field in there. Next, there's going to be the value, which will be, if it's a string, it's going to go ahead and be a byte array that's character encoded is going to be what it is. If it's a double, it's going to be a 2-byte integer. If it's in 64, it's going to be a 2-byte floating point integer. In 64, 2-byte non-floating point integer. You get the idea. So we go ahead and define our messages and also our state objects using this protobuf syntax. And through the protobuf compiler, that will go ahead and generate a C# object that looks like this, where all the properties are just basic POCO classes where I can go ahead and assign them. They all map to an equivalent CLR type. And we're going to go ahead and return this messages.ask. And this message can be very easily converted into a byte array. And that's ultimately how it will be transmitted over the wire. We'll take a closer look at how to implement one of these Akka.NET serializers that actually performs this translation when we do our demo towards the end of the video. But this is what you get as the output from that protobuf object. Now, in the past, the way the protobuf compiler worked, you essentially had to download a separate NuGet package from Google in order to compile these proto files into C# objects. There is now tooling that is built directly into ASP.NET that'll generate these message classes for us. That's what we're going to use in our demo as well. So I'll show you that too. Now here's where the power of versioning enters the picture with Protobuf. If I go and add a new field like this, in this case we're just using a new Boolean field, what's going to end up happening is when that new message type is transmitted over the wire, if I see this property I don't recognize, I'm going to go ahead and ignore it. And I'm essentially not going to throw an error. I'm just going to drop that piece of data because I don't recognize it. So the old nodes are essentially not going to do anything with that new data that they don't recognize. In practice, you want to avoid this because this is data loss. It's the same issue that we had with records. What you would typically do is roll out your updated library to all nodes and use a feature flag to stop any of those new pieces of data from being populated until the upgrade had been fully complete. Or you do what's called a two-phase upgrade, where you deploy the new wire format first, then you deploy the code that uses it second, which would be another approach for handling it. But the real scenario that we care about isn't necessarily this forwards compatibility here, it's backwards compatibility. Where if an old node sends a message to a node running the newest code, I should still be able to handle that. I should essentially provide a default value for whatever that new property is that's missing. So, node C has no idea about that on margin property. So when node A gets it, it'll substitute a default value, which will probably be, false in this situation or null or something. And that allows us to safely handle messages from older code. The reason why this backwards compatibility is so important is because you're going to have messages that get persisted and are saved to, let's say, an event store, and those messages are going to be at rest for years potentially. So you need to have a strategy for allowing newer code to read older data, and Google Protocol Buffers kind of has a built-in method for doing that, and that's very useful to us. So the built-in method that Google Protocol Buffers recommends and encourages is extend-only design, which is something that I've talked about before on my blog at length, and I'll link to that post in the description here. Extend-only design is the safest approach to versioning state and messages, and this is where all of the backwards compatibility guarantees come from. To preserve backwards compatibility, anything that's been introduced into our wire types, so any property, any type, it never changes. We can't rename those properties, we can't remove them, and we can't repurpose them, or we can't alter them in other ways, like changing the type of a property is something that we can't do. Once it is introduced to the schema, it stays there forever. So this is the whole idea behind extend only. It means that any of the destructive types of refactorings, meaning like deleting properties or moving them to a new type or renaming them, is simply not doable in extend only design. You can always add new properties or types instead. So you always should feel free to extend existing types that are there or introduce new ones, but we can't change the meaning of previous types that were introduced. So if you wanted to do a major refactoring in extend-only design system, what you'd probably do is introduce a new type and design it so messages of the old type could still be read and could still be mapped using the mapping layer we're going to introduce in the next part of our demo. You can still always map them back into whatever the new application type is, but you would essentially stop using the old types that were obsolete and begin using the new ones, but still make sure you have that adapter inside your read side of your system that could translate those old events into newer ones, could essentially upgrade them to the newer event type. That would make it so you wouldn't have any data loss issues inside your system, which is the reason why we're talking about this ultimately, is to make it so it's safe for us to continually change and modify our wire types without any negative consequences like data loss or data corruption. Now, one really important facet of extend-only design is that the new properties have to be optional. If this were not true, we would have deserialization errors, and the system would be brittle, and we would not have backwards compatibility. So we have to model our system from the point of view of anything that is new that is introduced needs to be considered an optional property. Otherwise, we can't upgrade those old messages that don't have that property into our existing type going forward. So this means that you have to reason about what the default value is going to be. Your deserialization layer or your application layer are going to need to have some way of handling that default. And so, in a lot of cases, that might mean just nulling out a property or maybe providing some system default that's specified in configuration. We'll take a look at that in our code sample in a moment. Now let's talk a little bit about the overall versioning strategy we're going to try to use. The biggest facet of it is that we're going to separate our wire types explicitly from our application types. They're going to exist as two discrete CLR types ultimately. The wire types are going to be defined in Protobuf, and they're going to be compiled into C# using the ASP.NET gRPC tooling to do that. So that's the first dimension of it. And then we have our application types in C# and F#. Now, in theory, you could have your wire types also be your application types where you're using the protobuf message format directly in your application. I've seen customers do that successfully before at scale in Akka.NET and really high throughput event-driven systems. You can do that, but it's a little cantankerous because, as I mentioned earlier, protobuf really limits you to a degree on being able to take advantage of some of the object-oriented programming constructs that are built into C# and F#. Good example, decorating your types with interfaces is something you would have a very difficult time doing since Protobuf doesn't inherently support that. So that's why I typically have two discrete types, and there's a translation layer we're going to build between them. Now, one other thing that having two discrete sets of types allows you to do is allows you to compress the number of application types that can fit into a single wire type. Where essentially, rather than having a one-to-one mapping between our application types and our wire types, we can take a bunch of similar application events or commands and represent them using a single wire type if we want to. My last company, Marked Up Analytics, where we were building a multi-tenant marketing automation and analytics system, because we built an SDK for users where they could go and define their own discrete events with their own discrete properties and everything else, we had to get really good at coming up with a generic way of reasoning about those events on the wire. Our SDK required it. And that was a very useful exercise. People are a little bit more lax about doing that inside private business applications that don't have to expose a public API to customers or partners or suppliers. But you should still bring that type of discipline to your design here, where rather than having, let's say, 30 different events for reasoning about changes to a customer's order, maybe you have one event that has enums and other types of, let's say, content-based payloads that can allow you to distinguish between them. You don't really have to worry about type safety here because there's a single layer of your application that's going to be responsible for translating that data into meaningful application types. Type safety is much more important to reason about inside your user code than it is in the way you're representing data over the network or inside your database. So that's why I kind of insist on trying to compress the number of unique wire types you need. This will ultimately make the exercise of versioning and evolving your schema a lot less expensive in the future if you do this early. And then finally, we need to create an explicit serialization and mapping layer between the two. Akka.net makes this very easy to do. You can actually go ahead and target specific types of messages and say these are handled by this serializer and these other messages are handled by this other serializer over here. This makes it very easy to modularize different parts of your domain and give them their own, let's say, discrete implementations for how to handle serialization there if you want. So that way you don't have to have some giant monolithic serializer that handles everything. You can break it down and distribute them as individual NuGet packages if you want to. We need to go ahead and make sure that there's no synthesis or reflection from app types to wire. Using a library like Protobuf.net completely defeats the purposes of versioning. The reason why is that it's going to reflect on the C# properties or the F# properties and generate a protobuf definition from that. Well, now we're back to polymorphic serialization again, where all of the same deficiencies that can happen from allowing developers to make changes to the application programming model without understanding what those side effects are in the wire model. Well, now we're back to that scenario again when you use a technology like protobuf.net. So you want to go in the opposite direction. Your wire types can't be changed by accident by making changes to your application type. So reflection is just banned from this whole system going. We're not going to use it. We're not going to synthesize our wire types from there. We're not going to get cute. We want to go ahead and make sure that if someone makes an incompatible change in the application layer, that should blow up at compile time if we've done this right, because they didn't go and update the mapping. And we should make it very expensive for someone to go and accidentally change the mapping layer. This is all designed to create data safety. That's what we're trying to preserve here, not ease of use by the programmer. We want to make sure that the data layer can't be corrupted by accident as a result of one developer being overzealous with a refactoring tool of some type. That's the entire reason we're doing this in the first place. So without any further ado, we're going to go ahead and take a look at a more complex demo that successfully uses Protobuf to manage its message and state versions. And we'll see what doing a rolling upgrade might look like in that scenario. All right, so for our demo, we're going to use the Petabridge/Akka.net code samples repository. This is public, and we've recently rewritten all the samples in here to use .NET 6 and other, let's say, sort of most recent best practices in .NET. So the sample we're going to use is this first one, Akka.cluster sharding with Akka.persistence.SQL server and Razor pages. Let's go and open that up. We have three different projects here, a headless service, a shared library that contains all of our infrastructure and configuration bits, and then we have our web application. So the web application and the host application are going to form a cluster, and they're going to use Akka.persistence.SQL server to event source state that is coming from each of the different actors in the host system. And if you scroll down here, you can see some of the technology that we're using. It's all .NET 6. We're using record types, which we mentioned earlier in this video. And we're also going to be using Protobuf for actually defining our messages and state. So I've gone ahead and I've launched this sample inside Writer. And we can see what the web UI looks like at the moment. So there's no available products, so we have no data yet inside our system. So I'm going to go ahead and create a new product. So I'll go ahead and call this Eagle Rare. It's a type of whiskey. MSRP, I believe, is $25 a bottle. And we'll say there's a 10,000 of them. So I'll go ahead and click submit. All right, I can see this data showing up. Now I'll go ahead and place an order for it. I'll go ahead and order a quantity of 100. Okay, so you can see that order record showing up. And I'll go ahead and place another order. Let's do a 25 bottle order here. Okie dokie. So we can go ahead and see some changes in our inventory. And if we go home, we can see Eagle Rare shows up inside our index. And I'll go ahead and add one more new product. Let's go ahead and do Weller Special Reserve. Price for this. And you know what? Just because I'm being a nerd, I'll go ahead and give it a specific volume. And we'll go ahead and price this at, I think this should be about $25 a bottle as well. And we'll say there's 1,000 of these. Press submit. We can see that. I'll go ahead and resupply it. I'll go ahead and add another supply of 100 bottles. You see we're up to 110 available units. I'll go ahead and order an additional 200. Place an order for that. And if we go home, we can see Eagle Rare, Weller Special Reserve, both showing up. So this is our basic application here. And the way everything is really structured, if I pull up Writer, is we have, let's see, let me get rid of our output window. I've got both applications running inside Writer, and I have SQL Server running inside this little Docker container right here. So what I have here is on the host application, we have these two actor types, the product index actor and the product totals actor. The product index actor uses Aggregate query. If I scroll down, we use this to go ahead and essentially look for new persistence IDs that are being added to SQL Server. And for each one that starts with this little prefix, we go ahead and we grab its unique identity, send it as a message to ourselves, and then we send a query to the Aggregate cluster shard region. Let's see, we do that right here to fetch that product information. We get that data back, we update our display data, and then every time one of the HTTP controllers in our web application wants to render all the different products inside our system, it'll send us this fetch all products message, and we'll go and convert this immutable dictionary into a list that it can render. And you can go ahead and see down here in the web app, if I go to our index page, open this up, you can go ahead and see that when this Razor page, which this is our root page of the website, receives a HTTP GET request, we go ahead and send a fetch all products message to our index actor, and then we get a fetch all products response back, which we then go ahead and render via Razor pages a little bit further inside the app here. I guess it would be up in this document is where we do that. So this is a pretty basic structure kind of showing how to combine, let's say, ASP.NET with Akka.NET. The really interesting thing we want to focus on is actually the product totals actor. We host one of these actors for every single product inside our system. So this is the actor that's responsible for keeping track of the state of our, let's say, Eagle Rare or Weller Reserve. That product identity is going to be what appears here as this actor's persistent ID. We're going to go ahead and try to take a look at some of the message and state formats that this actor uses, and we're going to attempt to version them. All right, so let's start by taking a look at how this actor recovers its state. So this is a persistent actor in Akka.NET. It has two different types of events it can process. Recovers, which are events that are deserialized from the database, and they're used to restore the actor's state when it's first either being reinstantiated on a new process or it's being restarted because maybe it threw an exception or maybe it got moved by Akka.NET cluster sharding from one node to another. Doesn't really matter what the circumstances are, the routine is the same. We're going to start by taking the oldest snapshot from the database, which is one of these product state objects. We'll explore that in a moment. We're going to go ahead and deserialize that directly from data that's stored in SQL Server. And then every single event that was recorded after this product state message, those will all be recovered here. These iProduct event messages. And the state object has a method that allows us to go ahead and process those events. And we use that for essentially reconstituting our state based on each of the different events that changed it over time. And then we have commands. These are live commands that are sent to the actor while it's up and running after it's recovered its state. And these commands can be transformed into one or more events. Some commands might produce no events. A good example, that would be a no-op or a deduplicated event. Might not produce any material change in state whatsoever. So we are going to call persist async on those events here. And this method will take all these response events, it'll save all of them using their sequence number in SQL Server, and then those events can be recovered again in the future to help reconstitute the state. Every 10 events, we're going to take a new snapshot. So a snapshot's like a point in time representation of the aggregate state of this actor. So when we talk about versioning events in state, what I literally mean is that these iProduct events are the events and messages that we have to version, and the state is this product state object. And we're going to use the exact same approach to version and save both of them. So this is our product state object, and this is what defines the aggregate state for each of those products we're looking at earlier. And I had a to-do from earlier that said we should add product inventory change records here too, since we currently don't display on the website whenever we get a resupply of an order. We don't actually have any way of surfacing that now, even though we do record those events. So I decided that maybe we should go ahead and add a set of inventory changes down here. And I already coded this in behind the scenes. So we just need to go ahead and add this assorted set of product inventory changes. However, as soon as I did this, I realized that we were missing an important piece of data on this event, which is unlike our orders where we record timestamps, we do not record timestamps for whenever inventory gets changed. So I need to update this event to include a timestamp property. This gives us a really great real-world example of how we can implement versioning both inside our state object and inside our events as well. So let's go ahead and start by taking a look at this event. As you can see, this is pretty simple. So we have a product ID, a quantity, we have our little reason here, but we are lacking a timestamp. So what we could do, similar to the product inventory warning event, or let's see, do we have a product sold event up here? I think we have a product order data payload, which yes, includes a timestamp. So we're basically converting date times into some sort of Google Protocol buffer field inside our serializer. We'll take a look at that in a moment. So let's start by adding this date time timestamp. All right, so we've included that. And you know what? I got to rearrange the parameters a little bit. Make that one go first. And I think writer is going to want me to do that. Okay. Oh yeah, well, it's going to complain at me because the application is currently running. So let me shut that down. And that should be totally fine. And let's see if we run into any compile time problems here. I'll go ahead and try compiling this. Stop and build. I thought I already shut everything down. That's okay. Well, here we go. And lo and behold, we've created one of these breaking changes inside our little record here. So now I could, if I wanted to, try to make this change source compatible by adding a constructor overload, but I actually kind of prefer that it broke my application events because I really want to make sure I'm passing in the right value into my application. So the first thing I'm going to do is do a new line here. We'll do datetime.utc now. All right, so that should do that. Let's take a look at any of the others we have here. Datetime.utc now. And let's see. Guess we should do that here as well. Datetime.utc now. These are all processing live commands, therefore it's totally fine to go ahead and change this. Now, what do I need to do here? Product inventory changed. I do var timestamp. There we go. Okay, that looks good. Got the deconstruction working. And the next thing we need to do is update our serializer. I'm going to hold off on that real quick. Let me go ahead and make sure that all the other compilation errors have been fixed. They've all been fixed outside of the serializer. Okay, that's great. Let's go ahead and actually start next by taking a look at the Protobuf message definitions we have here. All right, so what we have here is our Protobuf file. This will be compiled into some C# objects via some of the tooling from ASP.NET that we're using. I'll show that in just a moment. But we have a couple of various types that are common. And if we scroll down here, we can see this is our inventory changed event. Now, what we really want to do is we want to go ahead and add support for a timestamp to this particular event as well. So I'm going to copy this timestamp definition from up here, and I'm going to paste it onto the inventory changed event. So this will add a brand new optional property that wasn't there before. Now, the way this ultimately gets transformed back into our .NET application is if I take a look at the CS project definition for our shared library, you'll notice I'm taking a reference on this grpc.asp.NET Core NuGet package. This NuGet package will allow us to go ahead and generate C# classes from Protobuf definition files, so long as we add this type of reference, this Protobuf reference, to the file itself. So I'm going to specify the path to my SQL sharding.messages.proto file, and I'm going to specify that we don't have any gRPC services being materialized from this, meaning that this Protobuf file only contains message definitions. It doesn't actually contain any service bindings that use gRPC. After I hit compile, let me go ahead and do rebuild real fast. Well, that's still going to go ahead and fail because our message serializer hasn't been updated. Let's go ahead and take a look at our message serializer next. All right, so this is our message serializer class. Let me scroll to the top here and get rid of that. This is an Akka.NET serializer. Now, most Akka.NET applications tend to have only a handful of these for user-defined types, but internally within Akka.NET, we use several of them. And the way serializers tend to work is we implement the serializer with string manifest base class, and we represent all of the different wire types or application supports using a constant value like this. So CP for create product, SP for supply product. And so this is sort of shorthand for a type that we're going to parse from a byte array and turn into a .NET object. And then we also have this identifier, this integer right here. This integer is what uniquely identifies this serializer. So Akka.NET uses an envelope format, which has a tuple of serializer ID plus manifest. The combination of these two values tell Akka.NET which serializer to use and what message type this is, and we can go ahead and deserialize these types from the wire that way. In fact, if we take a look at the data that's stored inside Akka.persistence, so if I go ahead and run execute on this query here, this is our snapshot store table stored in SQL Server. And I can go ahead and see that the manifest is PS, and I can see the serializer ID is 556, and then this little bit of hex right here is our actual byte array. This is our Protobuf message saved as a byte array inside SQL Server. And so if I see PS plus 556, Akka.NET's going to know that 556 matches this serializer, the message serializer that's part of my application. And when it sees this manifest, which is PS, product state, what's going to happen is when Akka.NET basically receives a payload from either Akka.persistence or from Akka.remote, it's going to pass in the byte array that belongs to this serializer and that manifest. We are going to look for that product state manifest down here. Let me see if I can find it. Product state manifest. Here we go. And we're going to go ahead and call this proto.productstate parser.parsefrom. And this is going to generate the C# representation of my Protobuf type. So if I take a look at my Protobuf file here and you scroll up to the top, you'll see that the namespace that we're generating is SQL sharding.share.serialization.proto. That's going to be where this type comes from, proto.productstate, etc. And then this is a standard Protobuf method here for being able to transform a byte array back into one of our types. This is how we perform deserialization. The way we perform serialization on the right side is we receive an object, we go ahead and run a little switch statement on it, and when I see it's a product state, I call to proto down here, and I populate all of the different little members of my sort of state object here, and I return this Protobuf message definition, and that is going to be converted into a byte array. And that's what Akka.NET is going to write out to Akka.persistence or to Akka.remote. So this is the basics of our serialization layer here. We're going to define this serializer, and we're going to register this serializer right here. Using Akka.hosting, we're going to tell our actor system to use this serializer for all events and, well, really all events and all classes that implement this ISQL sharding protocol member. So as long as we decorate any of the state objects or any of the messages that we want to use with this serializer for with this interface, then Akka.NET will know to automatically route it to this serializer here. So that's really kind of the basics of how Akka.NET serialization infrastructure is able to separate certain message types to be handled with one serializer versus message types that don't implement this interface might be serialized by another. That's how we handle it. Now the trick is we need to go ahead and update our C# type, our little application record. We need to go ahead and update that to include our new date time properties. Let's go ahead and look at our compilation problems from earlier. And we can see here that we are trying to deconstruct our record, but we're missing one of our types. So I need to go ahead and add my timestamp here. Timestamp. Okie dokie. And so this is when we're converting to Protobuf. Okay. So let's see if my new Protobuf message definition has the property I'm looking for. And sure enough, it does. It definitely did not have this until we updated that Protobuf file and recompiled the solution. So if I change this to, let's see, timestamp, I believe that should work. Or do I need to call a little extension method? Let's see. I guess I need to go ahead and call, yeah, I think there's a little extension method I need to use. Timestamp from date time, timestamp. There we go. It's a little helper method that's Protobuf included inside our definition. So great. So now we're making sure that we save that date time. Now, if we don't have a date time, how should we go and handle that? Let's see. This is our this is our product inventory changed method. And we need to go ahead and make sure that if I grab, let's see, we're converting this from Protobuf. So I'll go ahead and do changed timestamp to date time. Okay. So I'm not sure what this method does when this value is basically left as more or less null. So we'll go ahead and take a look and see what happens. All right, so I'm going to go ahead and try compiling my solution, and provided that that all works, we'll go ahead and run it and see what the backwards populated data is for this. Although, you know what? I think there is one more thing I need to add. If I go to my product state, and if we have our product inventory changed event, let's see, is this process event? Yes, so I need to do one more thing, which is I'm going to go ahead and do, let's see, what's the name of my new property now? If I scroll up, I called it inventory changes. Okay. Totals equals totals. This will be inventory changes equals inventory changes dot add. And I guess, unfortunately, we're deconstructing this, so I really need to go ahead and add my product event. I need to cast this back into product inventory changed. That'd be useful if I could add a binding. Let's take a look at this. Ah, perfect. I can add a binding. Hell yeah, that's great. Okay, well, that simplifies things. So this should allow our data to show up. Now, we still haven't gone through and updated our state definition in Protobuf either. That's something else we're going to need to work on. But you know what? We'll roll with this for the time being. So let's see what happens when we go and deploy a new version of our application that now is able to display all these product inventory changes. What's going to happen with the old events that don't have that timestamp defined? If we've done our work right, and if Google Protocol Buffers handles that null case gracefully, we should go ahead and have some events that don't have any timestamp, but they don't throw an error either. Let's go ahead and run the application and give that a shot. All right, so I went ahead and ran the sample just now, and get a load of this. We have these null reference exceptions being thrown. And the reason why this is happening is the timestamp type in Protobuf is a class, whereas in .NET it's a struct, and in a struct in .NET is non-nullable, right? Whereas this class is. So we need to go ahead and add inside our serializer a handle for this. So if I go down here, the issue is when we're deserializing from proto. It's this method call is what's throwing the exception here. So basically, I need to have some default value in the event that this date time just doesn't exist. So what I'm going to do is add a little pivot there. And I'm going to go ahead and do date time dot, well, we'll go ahead and say min value. And that min value will basically be something we look at inside our display code. Let's see, sources are modified, changes will be applied on next step or resume. That's great. I'll go ahead and click apply changes. Now I'm probably going to have to restart the application to fix that, would be my guess, since that data has already been rehydrated. All right, let's take a look at this. At least one object must implement IComparable. Okay, that appears to be a bug with my product inventory changed event. We'd never implemented that. So let me go ahead and shut the sample down. Reason why this is a problem is this is a sorted set, which requires those events to implement IComparable, which they currently do not. So let's fix that. Go ahead and have this implement IComparable. Product inventory changed. And the way we'll go ahead and fix that, very similar to our product order. Actually, I guess we did this with product sold. Great, yes. Okay, let me go ahead and implement that method. And we really want to go ahead and just compare the timestamp. We don't care about anything else. Okay. Compare to. Great, that looks good. Okay, that should fix that issue. And let me go ahead and try running this in debug mode. And we should see all of our state get recovered without any serialization failures this time, which we did not get. Okay, so we have now fixed that problem. That is fantastic. All right, so I've gone ahead and have updated my Razor pages to include some handling for old events that don't have a timestamp defined. You'll see that the default value that we were passing in when we would deserialize an event without a timestamp was we'd use datetime.min value. So whenever I see that appear here, I just put a little NA for timestamp, and then I include the rest of the data that we do have. And whereas if that value is available, then I'll go ahead and actually display it. In fact, I should probably surround this in square brackets just so we're consistent. So I've gone ahead and I've done this already, and I've run our sample and launched it. And get a load of this. So I'm going to go ahead and reload the page. I've done a bunch of resupply of our products, but you'll see that none of our resupply data is showing up down here, even though we know for a fact that there is data that does support this. In fact, if I go and add a resupply event right here, you'll see that we're at 1218 right now. If I go ahead and resupply up to 30, we're at 1248, and there's no resupply change down here. So what gives? Well, the issue in this case is that if I go to my code behind here, when I send a fetch product message to the sharding system and my product totals actor receives it, the fetch result that we send back includes a product state. And this product state, if we take a look at our Protobuf message, currently does not include any definition for those inventory changes. So that's going to need to be the next thing that we change. In fact, I'll go and shut down the application here, and we're going to go ahead and fix it by doing the following. Let's see. The name of this event type is inventory changed. Okie dokie. So I'll go and add that. And I'll go ahead and do repeated. This is how you do a collection. Inventory change. Inventory changes equals 5. So this will add support at a wire level. Now I'll go ahead and compile this. This should go ahead and generate our new Protobuf definition. All right, that's great. And now I'll go back to my serializer, and I need to take a look at our product state handlers. Let's take a look at, let's see. This is when we're going from Protobuf, so I'll go ahead and go to the from Proto method here. And we'll go ahead and say that our inventory changes equals proto state dot inventory changes dot select from proto C, and we'll say to immutable sorted set. Okay, that looks pretty straightforward. And then I need to convert this bit right here. I need to go ahead and say, all right, proto state dot inventory changes dot add range state inventory changes dot select. That should do it. So all that existing code that we defined before for handling inventory changes, we're going to reuse all that here for defining our new updates to our product state object. So I'm going to go ahead and compile the solution here. This should all run without any issues. Great. So let me go ahead and start by launching our host. And you know, one thing I'm going to do to kind of make it a little easier on us, since our old snapshots, and by the way, snapshots, there we go. So we've got snapshots for both of these different products here. Snapshots are basically just represent an aggregation of all of the events for a particular object. They're a point in time representation of that state. As long as we aren't deleting the original events themselves, we actually don't need these. So I'm going to go ahead and do is edit the top 200 rows. Let me go ahead and grab this real fast. And I'm just going to go ahead and delete that row and delete that row. Okay, great. Rerun that. Now all the data is gone. Perfect. So this will go ahead and force us to rebuild that product state from scratch again. So let me go ahead and run our host. All right, host application's up and running. And let me launch our web app one more time as well. Okay, let's go back to our UI and I'll hit reload. And what do we have here? Conversion from date time to timestamp requires the date time to be UTC. Okay. And so this issue probably occurred. We're converting to Protobuf. And looks like we have, I see what the problem is here. Okay, so let me go ahead and shut this down. Let's see, date timestamp to universal time. Let's see if that fixes it. Go ahead and run that. Okay, and let's go ahead and try running that. Again, that should be a no op if we're not already. Go ahead and reload. And there we go. We can go ahead and see down here that our event looks like we did not do NA when we're missing that, but you can go ahead and see that all of our events are now appearing. If I go ahead and order a new one, let's go ahead and pump up, let's say 100. I go ahead and see our supply increase events here. If I do an order, let's do 250. I can see here that we lost 250 units to fulfillment. And let's go ahead and try another 1200 here. All right, there we go. And I can see that we're now on back order. Let's go ahead and resupply to 102. Now we're back to 0. Let's go ahead and add another 100. And there we are. So let's see, how many total events are we up to? Looks like we've got a sequence number at 20 again, and we should have all of our events persisted behind the scenes. If I go back to equal rare, I'll go ahead and see that we have some of our original supply increases here, and I'll go ahead and add another resupply, and I'll go ahead and do another order for 1440. All right, it looks like everything's working. So we've been able to successfully introduce these new changes to both our state and to our messages. And the way we went about doing it was essentially, this is by the way, actually a fairly difficult computer science problem, being able to version your state in a way that is safe and doesn't result in data destruction, like we were just able to. And the trick to doing it was being able to essentially be able to make sure that no old data was accidentally destroyed or its meaning changed in the process. We're able to extend the types to include these new properties. We're able to go ahead and register them in the serialization system of Akka.net. And we did have to do a little bit of trial and error. Normally, in an application that I was building for real, I would have unit tests that allow me to go ahead and discover this. But since we were just doing this via just trial and error with a little demo application, we found it via the debugger. So this is the general process for being able to work with message and state versioning inside Akka.net. So just to recap our methodology and our approach that we just showed today. So the first is to define our events and our other types inside a proto file. And then we can reference that proto file using the grpc.ASP.NET Core tooling and the Microsoft Build project definition to automatically generate C# Protobuf models for us. And then in Akka.net, we add a custom serializer with a string manifest. We register it to go ahead and convert between our application types and our wire types. This gives us that separation of concerns that is so important to making all this work well over a long period of time. And then finally, we also go ahead and use a marker interface to decorate all the classes that should be handled with this serializer. So if you're building, let's say, a modular set of services using a technology like Akka.net, you would probably have one serializer for each of your different domain types. And you have some common NuGet package that you can reference internally to add that serializer definition to your application. This is a pretty nice sort of modular approach to being able to deal with something like versioning and serialization across multiple different domains within your business. So thank you very much for sticking with me for this presentation. This is one of the longer videos that we've made. But if you need any help designing scalable and event-driven systems in .NET yourself, I strongly recommend that you contact us. You can go to petabridge.com and get access to training, consulting, or even implementation services from our team and partners here at Petabridge. And also, if you're interested in learning about Akka.net and you've never been exposed to it before, please head over to learnakka.net and you can sign up for our free Akka.net bootcamp and start learning how to build these types of distributed event-driven applications yourselves. So thank you very much for your time and look forward to seeing you for the next one. Thank you very much.